welcome to our Week 10 Discussion Board Team Solutions video. This is being presented to you today by myself, Heather Barton, and by Samantha Romero. This week, our discussion, Logic is Not Dry, involved a circuit that we would create which would activate a dehumidifier given three conditions. The first condition was that the humidity in the room must exceed 20%, and this would turn the dehumidifier on, but the container that holds the captured moisture must also be less than 3/4 full. Likewise, whenever an override button is pressed, the humidifier will turn on regardless of the humidity and the volume of the container. From here, we can create three simple propositions and present them as P, Q, and R, P being the humidity in the room, Q being the container holding the moisture, and R being the override button. Using these three conditions, we will create a truth table as seen here with an outcome based on these three conditions. Of course, in generating the outcome column, we also have to be careful to remember that P and Q will only result in a one outcome, meaning that the dehumidifier is turned on, provided that both of them are true. From our truth table, we can figure out minturns. A minturn is any row in a table in which you can write an AND expression to generate a one signal. As you can see, from our truth table, we can generate 5 of these. And these expressions are all using the values of AND for each condition that would turn the dehumidifier on. So you can see we've got P and Q and R, or P and Q and not R, or P and not Q and R, or not P and Q and R, or not P and not Q and R. Using our minturns, we can then create a circuit graph to show us what conditions would turn our circuit on and turn the dehumidifier on. We don't really need to create a graph that includes the conditions that would leave the dehumidifier off, since the dehumidifier is naturally in an off state. Here you can also see we're using our AND gates in the shape of Ds and our OR gates in the shape sort of the Star Trek symbol. Likewise, we've used a graph here created using circuitverse.org that allowed us to demonstrate what a particular run of this circuit might look like, hence the different shades of green and the different values next to P, Q, and R. This isn't demonstrative of every possibility, but just an example of how one particular run-through of the circuit might go with one of our minturns. Finally, of course, you can see our minturns listed out from top to bottom just before the final OR gate, which leads the circuit to turning on. Another way of drawing a circuit graph, one that might be easier to read, is to list out all of the different P, Q, and R statements, which would result in the circuit turning on. This way, there isn't so much overlap, and you can see more easily where our not statements are and how they relate to our minturns. This is also another way of drawing a circuit graph. Now, you might have noticed that our circuit graph had a lot of gates. We had more than 10. There is a way to simplify this, and if we wanted to, we could try to use logic to do so. But as it turns out, Maurice Carnot in 1953 created a method for doing this, which is visual and maybe a little bit easier than using logic. To create a K-map or a Carnot map, you create a table which includes all of the values of your conditions, and particularly all of the different values of those conditions from within your minturns. Here you can see we've got our different P values along the left-hand side and our Q and R values coupled together along the top. Likewise, after indicating which of these were on our minturn expression with dots, we then can circle dots which are together in groupings to the power of 2. So groups of 2 or groups of 4, groups of 8. We then circle them provided that they are either horizontally next to one another or vertically. On our particular map, you can see that we've circled in the top left corner in yellow, values of P that were true in one line, and then we also have a larger circle of 4 dots that sort of connects together off the sides of the table. If you can imagine, they sort of reach around and connect to one another on the other side. That is an acceptable grouping within a K-map. What we can then deduce from these groupings is which of these values is always true, and that's a value that we know for sure we can keep in our simplified formula. So here we can see in our yellow circle, the P is always true. And likewise, the Q is always true. R may or may not be true. So we can exclude R, but we can say P and Q results in an on condition. From our green circles, we can tell, or rather our green circle, we can tell that R is the only thing which is consistently true among those four values. Thereby we know that R alone could also turn on our circuit. Combining these two conclusions, we can simplify our statement with P and Q turning the humidifier on, or R itself. Hence you can see at the bottom of our page here, P and Q or R, reducing our circuits from 11 gates to 2. Much easier to read. However, we would like to check our work to make sure we didn't, maybe misinterpret our K-map. And so we can put our simplified expression back into our truth table. As you can see here, applying our simplified expression to our conditions, the column for our expression is exactly the same as the column for the outcome. Thus we know that they are essentially the same expression and our K-map worked.